welcome to Chapter 7, Quantum Theory of the Atom. It has a complicated name, don't be scared. It's an interesting chapter. I'll try to make it simple for you. Let's find out what is this chapter about. First of all, we talk about light in this chapter. So we need to know what is light. Light is not just like as simple as we just see, okay, we turn on the light in a room and it turns on and we see it everywhere. Light has an electromagnetic wave nature. What is electromagnetic wave nature? Means that it has both electrical and magnetic properties. So we need to know first wave. Everybody knows wave, the shape of the wave, but let's go deeper in understanding the elements in wave. The first thing which is important for waves is the wavelength. Wavelength is the distance between the two peaks or the two troughs in a wave. We show it with the Greek letter lambda. It's this letter. We call it lambda. And the units can be either meter or a nanometer because that's a distance, right? Another element in waves is the frequency. You have heard about frequency, about radio waves and the stuff. We show it with letter nu. This is like a curved V, is called nu. It's another Greek letter. We call it nu. And it's frequency. Frequency means how frequently a wave passes through a certain point. The units for frequency are per second, which we show in s to the power of -1, or per second in the bottom of a fraction, or we also call it hertz, Hz. So let's have an better understanding of the wavelength and frequency. Look at these two waves that I have drawn for you. Which one of them has repeated more often? I'm sure you will choose the second one. You see it has repeated more often. So it has more frequency. It has repeated more frequently. Like, let's say through a certain point, let's just call it this point. Which one has repeated more? Of course this one. But which one has a higher wavelength? The first one, right? So it seems like there is an inverse relationship between wavelength and frequency. The longer the wavelength, the less frequent. As if like you are taking longer steps, so you reach to a certain point slower. But if you take the faster steps, then you will reach there faster and you have more steps, right? You can try it. Alright, so let's see, when we say wavelength and frequency and they have an inverse relationship, how we show this inverse relationship with this formula. I want you to keep this formula in mind. This is the first formula that you'll have in this chapter. If you have the two elements that, or the two factors, I don't want you to mix it with the chemical elements. When you have the two factors that are inversely related to each other, their product or their multiplication is going to give you a constant. This constant here is the speed of light, which is 3 times 10 to the 8 meters per second. So this is a formula that shows the relation between wavelength and frequency. Example of working on this formula. What is the wavelength of blue light with a frequency of 6.4 times 10 to the 14 per second? So frequency, which is shown in nu, is 6.4 times 10 to the 14 per second. Speed of light is 3 times 10 to the 8 meters per second. So you plug them into this formula. You're solving for wavelength, and wavelength is speed of light over frequency. If you do the calculation, wavelength is going to be 4.7 times 10 to negative 7 meters. And you can easily change this meter to nanometer if you are supposed to, by knowing that 1 nanometer is 10 to negative 9 meters. If you're not asked for a certain Unit, you can leave it in meters. Otherwise, if you're asked for the nanometer, change it to nanometer. Another fact about light is that we said light has a wave nature, electromagnetic wave nature. So besides that wave nature, it's been proved by photoelectric effect that light is composed of small packages, small bundles of light or electromagnetic energy, which are called photons. So it looks like these little blue dots that I put to represent the photons are traveling on the waves. That's the meaning of photon and the nature of electromagnetic radiation. Now, there is a certain energy assigned to these photons. How do you calculate the energy of photons? By this formula. E is h nu, E is energy, which is expressed in joules. H is called Planck's constant, is 6.63 times 10 to negative 34 joules per second. And nu is frequency, which is expressed in per second. Again, don't worry about the conversions. The conversions are always given, or the constants are also given. Let's work on an example to find out how to combine these two formulas together. The blue-green light of the hydrogen atom spectrum has a wavelength of 486 nanometer. So wavelength lambda is 486 nanometer. What is the energy of photon of this light? For energy, you have this formula. But you are given the wavelength, and wavelength is in this formula. So what you need to do is you have two ways. Either find the frequency from this formula first and then plug it in there. What I did here is I found frequency from here, which is C over lambda, and then plugged it into this formula, which is E is equal to hc over lambda. But if it is confusing for you, you find this frequency from this formula first and then plug it in there. Up to you. So if you plug in all of these, and don't forget that because the unit for let me change the color, because the unit for light, so speed of light is meters per second, you need to change this nanometer to meter first. By knowing that, again, 1 nanometer is 10 to negative 9 meters. Alright? Pause it and start working on it again on your own. Another concept that we need to know here is what we call a continuous spectrum, or you have it on your PowerPoint slides. I wanted to go over it. We call it electromagnetic spectrum. It's a broad band of all the frequencies and wavelengths that contains all of the wavelengths of light, from low to the highest. And you will see, if you pay attention, you will see a very narrow range of this electromagnetic spectrum is the visible light that we see with our eyes. But when you heat an atom, they start emitting some colors. That's what you are going to do in the lab when you work on your flame test of metal cations. When you heat some metal cations in the flame, you're heating the atoms. So the electrons, we said they are on the energy levels, right? Energy level 1, 2, 3, 4, and higher. So when you heat the electrons, let's say electron is resting on this level. You heat it, the electron gets excited. So this is called ground state. The electron jumps to any of these levels, depends on how much energy is given. So it jumps to another state which is called excited state, to the higher level. But it cannot stay in the excited state forever. It has to come back. Depending on which level is coming back to, it can be the same level or the higher levels. The energy emitted by this emission, this energy you learn is h nu. If this energy or let's say this wavelength and this frequency are in the range of electromagnetic spectrum, the visible light, our eyes can see it as a color. So one more time, you hold the sample inside a flame, the electrons jump. You excite the electrons jump from the ground state to excited state. On their way back to the lower levels, they have to emit the energy to go back to the lower energy levels, right? So this energy will be emitted if the frequency of that energy is in the visible spectrum range. Our eyes can detect them, and they are shown as the color. So each element has a line spectrum that only contains certain wavelengths of light. In your PowerPoint slides, you have some line spectra for different elements. Please look at them, and you will see, like for sodium, you will have a couple of yellow lines. This is called element fingerprinting, because for every single element you have a different pattern of colors. That's really interesting, and I'm sure you will enjoy that experiment by holding the metal cations in the flame, and you will observe a different color inside the flame. Alright, so we talked about transition of electrons between the states, right? Now, the energy which is assigned to these elements, to these, let's say, photons, is equal to, you can call it energy or energy change. If you need energy, it would be the absolute value of delta E. It will be more clear. I'm going on an example for you later on. You will understand what I mean. So energy change, for transition between energy levels, I told you the energy jumps from, electron jumps from one energy level to another energy level, or drops from higher energy levels to the lower energy levels. So this is the formula that delta E is minus RH 1 over NF square minus 1 over NI square. RH is called Rydberg's constant, and it is 2.18 times 10 to negative 18 joules. These will all be given in the exam. Don't worry about memorizing anything. NF is the final state that electron is going to. So if electron is jumping to the higher state, that higher state is the final state. And Ni is the initial state where the movement, the transition of electrons started. So let's work on this example. It will be more clear. What is the wavelength of the light? How do you show wavelength? With lambda, right? What is the wavelength of the light when the electron in a hydrogen atom drops from the 6th to the 3rd level? So can you tell me what is the initial energy level? The electron dropped, right? So the transition started from 6th level and ended in 3rd level, right? So Ni is 6, Nf is 3. Plug them into this formula, delta E. I will explain about the absolute value and E after that. So delta E is minus RH, minus 2.18 times 10 to negative 18 joules, times 1 over NF was 3, right? 3 squared is 1 over 9, right? And minus 1 over Ni. Ni was 6, 1 over 6 squared, which is 1 over 36. When you do this calculation, delta E will be minus, let me change it to delta E because I don't want it to be confused. Okay, so delta E, or energy change, is 1.816 times 10 to negative 19. That was a drop of electron, right? And we say electrons emit energy, release energy. So this negative sign is for releasing energy, and makes sense. It doesn't mean that this is a low amount of energy. It's just energy emission, right? So if you want to find lambda, you need to find it from E is hc over lambda, right? That's why we say E is the same delta E by the absolute value of delta E. Means you don't have to be worried about this negative sign here. Just use its absolute value in the equation that you knew from before. So you're solving for lambda. E is hc over lambda, so lambda is hc over E. Plug them in. You have two constants on the top of fraction, 6.63 times 10 to negative 34 times 3 to the 8 meters per second, divided by the energy that you just found. And lambda is going to be 1.094 times 10 to negative 6 meters. Please don't forget to work on different examples, and hopefully you understood this part. In the next part, I will work on the concept of quantum numbers.